When we got the very first signal from the atoms, it was some blurry picture that had some weird granular structure, and we got super excited. And then we spent some more hours trying to get this signal better.
We just basically started moving the camera little by little, and the blob was getting bigger and bigger. And at some point we were able to see the individual atoms appearing out of the noise of the picture, and this was a really nice experience.
And when in the evening we finally got the single atoms, we were super happy and yes, we finally achieved our goal and the hard work paid off.
I'm excited, science works, physics works, and all our attempts and efforts, they worked out.
Quantum gas microscopes are a device that exists for quite some years, like a decade, but there are only a few labs in the world that do that because these are complicated machines. There are, I don't know, about 20 labs or so. In our group, we are the only ones having this imaging of single strontium atoms that are in the quantum degenerate regime, really where atoms are behaving as waves and overlapping and so on, and you have interference effects, so macroscopic quantum effects arising. Strontium brings the novelty to the game that it has a more complicated optical spectrum, so you have more optical transitions you can play with, and this is what allows you to make super precise measurements like the ones that are used in atomic clocks, but also it allows you to image in a more easy and straightforward way, and it also, for example, can allow you to mimic materials that don't have only electrons in two states, which normally we call spin up, spin down, like two states for the electrons, but strontium you can have up to 10 states for these electrons, let's say, and then you have new phases and new physics that is expected to arise, and really much more computational power, let's say, if you want to use these machines as analog quantum computers.
So the optical lattice, you can imagine it like an egg cardboard box where the individual sides are actually where you put the eggs. So instead of eggs, we have atoms. Instead of this cardboard, we have an optical lattice. And one atom is not locally in the site, but it's smeared out over several lattice sites. And once we do the images, we are pinning the atoms in the locations and they collapse into the single lattice sites, and then we take the images.
We prepare our atoms in some specific quantum state, and when we take a specific snapshot of the atoms, they might look with some distribution that might a priori look random. And this is why we have to take several repetitions of the same cloud by repeating this process of cooling it down, preparing it, and taking the picture. And from that we can get enough statistics and, for example, average the density of the atoms in our system, as well as, for example, look for correlations between atoms. So what is the probability of having an atom here if I have another one there next to each other?
In order to get the atoms in this lattice and then to image them, we need to start with some stream of atoms. We send laser beams from 6 different directions to trap them spatially and also cool them. And then we do on top of that optical trap where we keep the atoms trapped, and we need to cool them further down in order to get the quantum regime which we want. And this, you can imagine this cooling process like blowing on your coffee, removing the hot particles, and then it gets colder, and it's essentially that process. It's called evaporative cooling, and that's what we are doing to get the atoms into this regime.
This is one thing I really like about ultra-cold atom experiments, that basically the complexity is so high that you can't really do, no one could do this alone.
It's a lot of work. There are a lot of things to address. I would not say that it looked impossible to me, but yeah, I understood that it was a lot of work to be done.
So in our case, the system they prepared, this quantum gas of strontium atoms, was in a superfluid state in this optical lattice potential. A superfluid is a state of matter that can flow without any viscosity. And in fact, it's very related to, for example, superconductors. That's in a way very similar to superfluids, but in a different system. And that meant that essentially the atoms were in some complex superposition of all these different lattice sites. We detected this property of superfluidity by performing an in-plane expansion of the cloud by just suddenly switching off the optical lattice. After the expansion, the cloud formed an interference pattern due to the wave-particle duality of the atoms that were in the superfluid.
allows us to image thousands of sites. However, for the quantum regime, in the end we have hundreds of atoms in a smaller regime because we lose some of the atoms during the cooling process. When we look at pictures of atoms that are taken consecutively, we sometimes see atoms hopping around. This is an effect called tunneling because they tunnel from one side to another one. And even though this is not what we want for imaging, this is something very beautiful to see because you actually see this quantum effect of tunneling from one side to the other.